Lighthouse Scientific Education presents a lecture in the mole series. The topic, the mole as a quantity. Material in this lecture relies on understanding of the previous lectures, dimensional analysis, and scientific notation. This lecture focuses on the mole as a counting unit. It begins with a look at other counting units that are more familiar to give some perspective. These familiar counting units are used to demonstrate how counting units can be formed into conversion factors. Conversion factors facilitate the changing of units from one type to another. Specifically, the definition of the counting unit is used to create unit factors. Conversion factors and unit factors are essential tools in dealing with moles, and the student should have a modest understanding of them moving forward in their study of chemistry. If this is already the case, then skip this subject and the practice problems that use familiar units in conversions. Then it is on to an introduction of the main topic, the mole. The definition of the mole is also used to create and use unit factors as conversion factors. The lecture ends with a quiz using the definition of the mole in conversions. Counting larger units. When common items are dealt with in large numbers, they are not counted individually. Appropriate sized terms that are called counting units are used for counting. For example, 12 eggs are generally counted as 1 dozen eggs. Dozen is a counting unit. Large numbers of eggs are counted in dozens. 24 soda cans is referred to as a case of soda cans. In this circumstance, the term case means 24. Consider a package of 500 sheets of paper. That is a large number, which is more easily handled as a ream of paper. In each case, a new counting term is used to handle larger numbers. Each term is derived from the practical counting or availability of the item. A ream of eggs is not a realistic amount to be sold in a grocery store. The value of the counting unit is only to reduce the size of the number of the individual count. Percent plays the same role with fractions. For example, 5 reams is easier to understand and process than 2,500. Plain and simple, collection terms allows for the use of smaller numbers. People feel more comfortable with numbers that they intuitively understand. We like our numbers to be between 1 and 10. Few people have an intuitive understanding of 2,500. Most first graders have mastered the number 5. We will return to these counting units in a moment, but first a review of conversion factors. Conversion factors are a tool for changing units of a measured or given value into different units without changing the value. For that to be true, the units in the conversion have to be the same type. That is, they are both units of a kind of measurement, such as length. Inches can be converted into centimeters, or units of weight. Grams can be converted into pounds. Moving between different units doesn't alter the amount or length. It merely changes how the amount is presented. 1 inch can equally be described as 2.54 centimeters. There is a conversion factor that mathematically allows the conversion. Conversion factors are covered in detail in the dimensional analysis lecture, which is part of the measurement in number series. Conversion factors will be reintroduced here because of its necessity in dealing with the topic of the lecture, moles. In the dimensional analysis lecture, the description for converting from one form of units to another form of units of the same measurement type used the generic terms of current units for the unit type before the conversion and desired units for the unit type after the conversion. The mathematical expression of a conversion has the given or the starting or the current unit type on the left-hand side of the equal sign, and the wanted or the desired unit type on the right-hand side of the equal sign. Following the current units will be the conversion factor. Its role is to change unit type and to provide the numerical difference between the units. Let's look at its first role, changing unit type. It does so by canceling out the term current units. To help clarify the process, which is going to involve fraction math, the current unit term is made into a fraction with a denominator of 1. Anything can be made into a fraction by dividing it by 1. What this highlights is that the term current units can be considered as being in the numerator of a fraction, even if it is not written in fraction form. Now, in fraction multiplication, if the same thing is in the numerator of one fraction as in the denominator of another, it will be canceled out. All that is left is the desired unit, and the equation is complete. All conversions will seek to cancel out current units, leaving desired units. That is the underlying principle of conversions. With that in mind, we return to those counting units and show how the definition of unit is used to create conversion factors. A conversion factor from dozen into number of eggs might look like 12 eggs over a dozen. 24 cans over one case is a conversion factor into cans from case, and 500 papers over one ream is a conversion factor into paper from ream. If the opposite conversion is wanted, then the conversion factor is the reciprocal. 1 dozen over 12 eggs will go from eggs to dozen. 1 case over 24 cans goes from cans to case, and 1 ream over 500 paper would go from paper to ream. The reason that these ratios or fractions can be used as conversion factors is that in each and every case, the ratio is equal to 1. These conversion factors are known as unit factors. A unit factor is a fraction that has the same value in the numerator as in the denominator and is therefore equal to 1. It will be helpful to describe the construction of a unit factor, since unit factors in conversion surround the use of the mole. Take this 12 eggs over 1 dozen conversion factor. Its construction begins with its definition as an equality, and that equality is 1 dozen equals 12 eggs. We could use donuts if we wanted to, but this is not about the object, it's about the units. To get a unit factor, divide both sides of the equation by the value on one of the sides. Here we will divide both sides by 1 dozen. Shortly we will return to this step and divide both sides by 12 eggs. For now, we have this modified equation. Since both sides are divided by the same value, we've maintained the equality. The final step is to solve or simplify the expression. 1 dozen divided by 1 dozen equals 1. There are no units. The dozens cancel out. Another way of looking at this simplification is to ask, how many 1 dozens are there in 1 dozen? That answer is 1. The other side of the equation that still remains is unchanged, and we have the unit factor that we set out to get. Taking a step back, we can construct a different unit factor by dividing both sides of the equation by 12 eggs. In simplifying this expression, we ask how many 12 eggs are there in 12 eggs, getting the value of 1. The other side of the equation is unchanged, and the second unit is produced. These unit factors are reciprocals or flips of each other. They both equal 1 and are therefore equal to each other. Any equality can be made into a unit factor by the simple steps of dividing both sides of the equation by one of the sides. We can solidify our understanding of conversions with a couple of examples. The format of the conversion, current units times unit factor equals desired units, will be our guide. First example, 60 cans is equal to how many cases? A setup of 60 cans is the current unit, and the case is the desired unit. What's needed here is a unit factor with the correct orientation of units. Bringing up the definition of the case, we construct the appropriate unit factor by recognizing the need to cancel out the current unit of cans. Since 60 cans is essentially in the numerator, the unit factor will need to have cans in the denominator. Inserting this unit factor and verifying that the units of cans cancel out gives us a correct mathematical equation for the conversion. Taking these values to the calculator and dividing 60 by 24 will give a value of 2.5 cases. 60 cans equals 2.5 cases. The next conversion gives 78 donuts and asks for the number of dozen donuts. Beginning with an equality, 12 donuts equals 1 dozen donuts, the correct orientation of the unit factor to be inserted in as a conversion factor will be the one that has single count of donuts, the current unit, in the denominator. The orientation of this unit factor is correct because the unit donuts cancels out, leaving the unit dozen. Proper use of the calculator will show that 78 donuts is equal to 6.5 dozen donuts. We see that it is a smart practice to literally draw a line through the units to cancel them out, because it double checks our orientation. Final conversion is 5.5 reams of paper into individual count of paper. Starting with the equality, 500 papers equals 1 ream. The correct unit factor will have the current unit reams in the denominator so that the current units cancel out, leaving the unit papers. The math is multiplication this time. The other two examples involve division. And the final answer is 2,750 papers. Students who are still not comfortable with conversions should review the dimensional analysis lecture. Now it's time to get after counting very small particles. Particles on the atomic scale are so small that vast numbers are required to even see them. For example, it takes about 1 times 10 to the 24th water molecules to fill a shot glass. That's how small water molecules are. As there is a need for dozens, cases, and reams, there is a need for a chemistry unit. The chemistry unit will have to be very large in order to bring the number of atomic scale particles into the realm of comfortable numbers. And it is. The mole is the counting unit for chemistry. To be inclusive, some textbooks shorten mole to just MOL. Either way, they both represent the same thing. That is a number. It is a counting unit. Counting units reflect the size and dimension of particular items. Dozen is used for items that are the size that regularly come in 12. The case is for items that regularly come in 24, and ream for items that regularly come in larger collections like 500. The mole is used for items that come in very, very large numbers. It is a number that is so large that it is easier to write in scientific notation. 1 mole equals 6.022 times 10 to the 23rd. Some textbooks just use 6.02 and not the 6.022. Either way, it is multiplied by 10 to the power of 23. 6.022 times 10 to the 23rd is called Avogadro's number, after the Italian scientist Amedeo Avogadro. Additionally, the symbol N subscript A is used for Avogadro's number. So there are 4 ways to express this value. 1, 6.022 times 10 to the 23rd. 2, just calling it a mole. 3, calling it Avogadro's number. And 4, that shorthand N sub A. Avogadro's number will follow us the rest of the way through the study of chemistry. Just how big is 6.022 times 10 to the 23rd? Well, 6.022 times 10 to the 23rd seconds is 14 quintillion years. That is 1,000,000 times longer than the existence of the universe. A mole of pennies would be a stack that made 3.5 round trips to the moon. There are about N sub A milliliters of water in the Pacific Ocean, the entire Pacific Ocean. Note that we use 3 different representations of Avogadro's number, and also note that Avogadro's number is an inappropriate unit for time, coins, or any amount that we can see with our eyes. But Try this out. How much is 1.66 moles of the molecule H2O? It is that shot glass of water, which we saw contains 1 times 10 to the 24th molecules of water. So the mole is a good counting unit for subatomic particles, like electrons, protons, neutrons. It is good for atoms, ions, molecules, and compounds. It is good for atomic scale particles. An expansion on the notion of moles comes when dealing with compounds. We know that the molecular formula, or the formula unit, gives the ratio of atoms or ions in the compound. 1 mole of a compound will therefore have that ratio of moles of atoms or ions. For example, 1 mole of the compound barium chloride, BaCl2, will have 1 mole of Ba2 plus cations and 2 moles of Cl minus anions. That follows from the formula unit ratio of 1 barium ion to 2 chloride ions. 1 mole of the polyatomic ion CO3 minus 2 carbonate will have 1 mole of carbon atoms and 3 moles of oxygen atoms. The minus 2 charge plays no role here. 1 mole of carbonate has 4 moles of atoms. 1 mole of the sugar molecule C6H12O6 will have 6 moles of carbon atoms, 12 moles of hydrogen atoms, and 6 moles of oxygen atoms. Some math with these numbers show that 1 mole of C6H12O6 is comprised of 24 moles of atoms. This is consistent with the sugar molecule having 24 atoms. As with other counting units covered in this lecture, the mole can be made into a unit factor as long as it is a fraction with the same value in the numerator as in the denominator. Repeating the process of generating a unit factor begins with an equality. 1 mole equals 6.022 times 10 to the 23rd. Divide both sides of the equation by one of the sides. For example, divide both sides by 1 mole. Solve or simplify the expression. 1 mole divided by 1 mole is equal to 1. The second fraction remains unchanged. This is the first of 2 unit factors that can be used in moving between count and moles. The other unit factor is made by dividing both sides by Avogadro's number and simplifying the fraction on the right to 1 and leaving the other fraction unchanged. These 2 unit factors are equal to 1 and therefore are equal to each other. These unit factors can be put to work converting from individual count to moles or vice versa. They are based on the definition of a mole as a counting unit, but the count needs to be of something, like atoms. A mole of atoms is Avogadro's number of atoms. A mole is not a mole of atoms. A mole is a number. A dozen is not a dozen eggs. It is a number, 12. The unit factor based on the definition of mole should include what is being counted, like atoms. The first unit factor says 1 mole of atoms is equal to 6.022 times 10 to the 23rd atoms. But the mole is not just for atoms. The count can be of ions, which can be included in the unit factors. The second unit factor reads as 6.022 times 10 to the 23rd ions over 1 mole of ions. Same logic with the count of molecules. Molecules are added to the unit factor, producing a couple of equalities. The point here is that the mole is a number, not a number of atoms or a number of ions or a number of molecules. It is just a number. There is a general term that comes up in mole conversion problems. It is inclusive of atoms, ions, and molecules. It is the particle. A mole of particles is Avogadro's number of particles. Unit factors follow from the definition and serve to convert between number of particles and moles of particles. We will see that conversions using moles are fundamentally no different than those for dozens. Consider the conversion of 10 to the 24th atoms into moles of atoms. The definition of a mole of atoms leads to these two unit factors. In the problem, atoms are the current unit, and moles are the desired unit. Which unit factor is the appropriate one for the conversion? As with all conversions, that is decided by which factor cancels the current units out. Count of atoms is a current unit and can be considered in the numerator. Therefore, this unit factor has the correct orientation because its count of atoms is in the denominator and will cancel out, leaving the desired units of moles of atoms. What's left is a division problem, but one that involves some pretty big numbers. A review of inputting scientific notation values into a calculator might be helpful here. A more thorough demonstration of scientific notation with a calculator is given in the scientific notation lecture. Remember, different calculators can use different sequence of keystrokes. We will use a generic calculator to solve this problem. There are 2 points that need to be made before the calculation. The first is inputting the 10 to the 24th or the 10 to the 23rd. Most calculators have a button that specifically sets this up, so all that needs to be added is the exponent. On the generic calculator, it is the EXP button. Some calculators have that as an EE button. Here, it is the EXP button. The second point is that the 10 to the 24th is easier to input as 1 times 10 to the 24th. The division of 1 times 10 to the 24th by 6.022 times 10 to the 23rd. Input 1, then EXP button, the exponent 24 as 2, 4, divide 6.022, EXP button, exponent 23, 2, 3, equal sign. Now, this yields a very long number, but it begins with 1.66. The answer to the conversion is 1.66 moles. For completion's sake, we can reverse this problem and have the 1.66 moles of atoms as the given or current unit, and the count of atoms as the desired unit. A different unit factor is needed in this setup because there is a different current or given unit. Since moles of atoms is technically in the numerator, the correct unit factor will have moles of atoms in the denominator. Canceling out units leads to the count of atoms, which is the desired unit. A second calculator demonstration introduces a second helpful key. It is called the FE key, and it toggles between numbers written in decimal form and that same number written in scientific notation. Really small and really large numbers are difficult to read in decimal form. The math of this equation, 1.66 times 6.022 times 10 to the 23rd, is done by first inputting 1.66, hit multiply, then 6.022, go to the EXP button, and hit the exponent 23, and then equals. Now, go back to the FE button, which brings it back to scientific notation. We have 9.99 times 10 to the 23rd. We will round this term. 9.99 times 10 to the 23rd rounds to 10 to the 24th. Practice these two demonstrations on your calculator to verify the necessary sequence of keystrokes that will get the appropriate answer. This lecture ends with review in the form of a quiz. The definition of the mole and the 2 unit factors derived from the definition will be our key to solving the following conversion problems. The first problem, calculate the number of moles that contain 3.5 times 10 to the 24th molecules of H2O. Identification of this question as a conversion problem is the first step. Determining the given value with the current units and the wanted value with the desired units is the next step. From the question, we see that 3.5 times 10 to the 24th molecules is the given value, which is written on the left-hand side of the equation. And moles of water is the desired unit, which is written on the right-hand side of the equation. The selection of the appropriate unit factor is the next step. The unit factor must have an orientation that cancels out current units, which is count of molecules. Inserting the unit factor and verifying its correct orientation by canceling out count of molecules leaves the desired units of moles. Correctly entering the numbers of this division problem into the calculator will yield a value of 5.8 moles of water. 3.5 times 10 to the 24th molecules of water is 5.8 moles of water. A second problem asks us to find the number of protons in 2.88 moles of protons. Again, we identify this question as a conversion problem. A close look at the problem shows 2.88 moles of protons to be the given or current units. Insert that value on the left-hand side of the equal sign. The desired unit is the number of protons. Insert that on the right-hand side of the equation. Since the current unit is moles, and it is technically in the numerator, the correct unit factor that will cancel out moles must have moles in the denominator. Like this. Indeed, moles of protons cancel out, leaving count of proton. The calculated solution comes to 1.73 times 10 to the 23rd protons. The final question is one involving the generic term particles. How many moles of particles are there in 2.0 times 10 to the 22nd particles? Identify the question as one of converting between units and set up inequality. Referring to the problem, we see that the given units are numbers of particles, which we write on the left-hand side of the equation. The desired units are moles, which we write on the right-hand side of the equation. The conversion between number of particles and moles of particles requires the definition of moles in the unit factors that follow. The unit factor that completes this conversion has to have Avogadro's number of particles in the denominator, so that count of particles cancels out with count of particles as a given unit. This leaves moles of particles, which is the desired unit. The calculated answer is 0.033 moles of particles. A lot better than dealing with 10 to the 22nd. To recap the lecture, when items are dealt with in large numbers, they are not counted individually. Appropriate sized terms, counting units, are used. This is solely done to bring numbers into a more comfortable range. The mole is a number. It is a very large number, which can be represented in scientific notation as 6.022 times 10 to the 23rd. Some textbooks will use the coefficient 6.02 instead of 6.022. Being such a large number, the mole is only used with atomic scale particles, such as subatomic particles, atoms, ions, and compounds. For 1 mole of a compound, the molecular formula, or the formula unit, gives the ratio of the moles of the atoms or ions that make up that compound. Conversion factors are a tool for changing units of a measured or given value into different units. These different units are referred to as the wanted or desired units, and have to be the same kind of measurement. Conversion requires a unit factor. This is a fraction that has the same value in the numerator as in the denominator, and is therefore equal to 1. In a conversion, the unit factor is oriented such that the current units cancel out. That concludes our lecture. The mole is a fundamental concept in the study of chemistry. Make mole conversions a tool, and it will greatly reduce the complexity of future topics.